let's say that I have this green container, and inside this green container I have some air molecules. Now the air molecules, we assume that there's some temperature, there's some average kinetic energy to them, but they're all going to have different velocities, they're all going to be bumping around in different ways. Now the way that I've drawn it, you might notice something. On the left-hand side, and I'll just draw an imaginary line here. This line has no real, I guess you could say, structural significance. It's not like it's actually dividing it. I'm just using it to visualize the left and right-hand sides. You see on the left-hand side, I have a higher concentration of my molecules. Higher concentration. And how do you measure concentration? Well, the number of molecules per, well, the really way you should do it is unit volume, but we're looking at a cross-section here. If I were to take a section that large, look, I got 4 molecules here. It looks like I have about 3 to 5 molecules per section around that size. Well, if I took that size section on this side, I'm getting 1 or maybe 2 molecules. And I'm not going to get too precise, but it's clear that I have a higher concentration here. I have more molecules the way I've drawn it per unit area, but if we were thinking in 3 dimensions per unit volume, than we have on the right-hand side. So we have a higher concentration on the left. We have a lower concentration on the right. Lower concentration on the right. And when you have this situation where you have a higher concentration and then a lower concentration, we call this a concentration gradient. The concentration is changing from high to low, and so we call this a concentration gradient. Now, what do we think is going to happen? Let's say this is what our situation is right when we look at it. What do we think is going to happen? Well, all of these particles are all going to be bouncing around. Things can move from the left to the right. Things can move from the right to the left. But we have more particles on the left that are likely to move to the right than we have particles on the right that are likely to move to the left. Remember, they're all moving in different directions with these random velocities, but I have more on this side, and they're all bouncing around. So in any given moment, when we have this higher concentration on the left, I have a higher chance that I'm going to have stuff go from the left to the right, than I do from the right to the left. And so as time goes on, it's going to look something like this. If we let this system stabilize, for a while, it should look like this. And let me see if I can do a good job drawing it. And I'll just draw the molecules. I won't draw their actual velocity vectors. So if we wait a while, how many molecules did I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So now I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So if we let enough time go by, we see that we should no longer have a concentration gradient, that the concentration should be fairly uniform over time. So even if I were to draw that imaginary dashed line, I should have the same concentration on both sides. So I no longer have a gradient. I have no gradient. And once again, there's nothing magical here. It's not like the molecule said, oh, we are less concentrated over there. I somehow have to know to move there. You just have to think that these are all just randomly bouncing around. And if you have a higher concentration on the left, there's a higher chance that you have bounces or you have things moving from the left to the right as you do from the right to left. Even in this situation, things are still going to be moving from left to right and right to left. But now that you have the same number on either side, in any given moment, in any given period of time, you have an equal probability of things moving from the left to the right as you do from the right to the left. So you're getting to kind of this equilibrium situation. Sure, in a given, if you take a certain unit of time, maybe that one moves from the left to the right, that one moves from the left to the right, that one moves from the left to the right. But since you have equal concentrations on both sides, you're just as likely to have the same number move from right to left. And I only did this with 20 particles, which is a little bit of an artificially low number. If we're actually talking about concentrations of air molecules, or as we'll see when we think about cellular membranes, if we think about different types of molecules that might be in an aqueous solution, we're talking about way more than 20 molecules. And so you really do think in terms of probabilistic large numbers. Well, hey, for the probability of something move from the left to the right is the same as the right to left, and so you're going to have the stability. Right here, there's a much higher probability in any given moment of something moving from left to right than right to left, and that's why you see things moving from high concentration to low concentration. Or another way to think about it, what we just observed here is we saw things diffusing down their concentration gradient. So this process that we just described, this is diffusion. This is diffusion. And as we study different types of systems, we'll see that this is actually very important to biological systems and even chemical systems, because this doesn't require any extra energy to move the molecules from here to there. This is going to happen probabilistically. It's going to happen naturally. And once again, no magic. Just more stuff here, higher chance moving from left to right than moving from right to left. And I really want to make that point clear. You can still move from right to left. For example, you might have this character, maybe instead of moving in that direction, completely possible that he goes from right to left. It's not like everything is moving from left to right, but you have a higher chance you're going to have more things moving from left to right. So that guy could move in that direction because there's just more stuff here, and they're all bouncing around in all different random directions.